November 23, 2025, people in Afdera, northern Ethiopia, woke up to a sound they described like a bomb. The sky didn't just turn grey, it turned white. A column of ash surged to roughly 45,000 feet, straight into commercial flight levels. And it didn't stay local. Upper-level winds pushed the plume across the Red Sea toward Yemen and Oman, into major air corridors linking Africa, the Gulf, and South Asia. Within days, airlines in India were cancelling flights and carrying out precautionary checks because ash at altitude doesn't respect distance, it respects wind. The source was Hayli Gubbi, a long-dormant volcano in Ethiopia's Afar region, with no recorded modern eruption. Some reports described it as erupting for the first time in nearly 12,000 years. And that's where the real story begins. Because Afar isn't just a place where volcanoes erupt, it's a place where the continent itself is under tension, and sometimes that tension shows up all at once. So why here? Why can the crust fail so quickly in this one part of Africa? And what does that have to do with the birth of a future ocean? To untangle it, we have to go beneath the surface, into the mechanics of how continents thin, crack, and over deep time become oceans. To understand why Africa is splitting, you first have to understand where the split announces itself. On a political map, your eye goes to the obvious shape, the sharp hook of Somalia and Ethiopia pushing into the ocean, the Horn of Africa. But switch to a topographic map and the story changes. A massive Y-shaped depression appears in the land as if the crust has been pressed downward and pulled apart at the same time. That Y-shape has a name, the Afar Triple Junction. It's one of the most geologically intense places on Earth because three plates meet here, and instead of colliding, they're all moving away. To the west is the Nubian plate, carrying most of Africa. To the east is the Somali plate, carrying the Horn. And to the north is the Arabian plate, which has already pulled far enough away to help open the Red Sea and the Gulf of Aden. Afar is the knot where those seams intersect, and the surface looks like the planet is showing you its stress in plain sight. The lowest part of the region, the Danakil Depression, drops below sea level. The ground turns blinding white with salt flats. Steam vents hiss out of fractured earth. And the heat is brutal, often pushing past 120 degrees Fahrenheit. But that heat isn't just coming from the sun, it's coming from below. Because the crust here is unusually thin, closer to a stretched skin than a stable continental slab. And when the crust is that thin, magma can intrude more easily, wedging the crust apart from the inside. That's why Afar produces these sudden moments. Earthquake swarms, fissures, eruptions. Each intrusion and each quake releases tension and widens the rift by another step. And this isn't guesswork. Satellites can measure the ground, subtly rising and sinking over time. So when we say Africa is tearing, this is where the sentence stops being abstract. In Afar, the split is written into the landscape, and it doesn't stop in Afar. From Afar, the East African Rift System runs south for nearly 4,000 miles, slicing through Ethiopia, Kenya, Uganda, Rwanda, Burundi, the Democratic Republic of the Congo, Zambia, Tanzania, Malawi, and Mozambique. Seen from orbit, it looks like a giant claw mark scratched diagonally across the face of Africa. But this isn't one clean crack. It's a system, and geologists describe two main branches that behave very differently. The eastern branch, through Kenya and Tanzania, is the more arid, more volcanic arm. This is where the rift announces itself, with mountains you can't ignore. Kilimanjaro, and Mount Kenya. And these aren't fold mountains like the Himalayas. They're volcanic giants, built by repeated eruptions, punching up through a crust that's thinning and weakening. The western branch, curving through Uganda and the Congo, is different. It's generally less volcanic, but it's defined by deep basins. As the crust pulls apart, huge blocks of land drop down, creating grabens, long, narrow trenches. Over time, those trenches fill with water and become some of the continent's most famous lakes. This is where you get Lake Tanganyika and Lake Malawi. And Tanganyika is extreme, over 4,800 feet deep, one of the deepest lakes on Earth, with its bottom plunging far below sea level. In a sense, these lakes are the rift made visible, water collecting in the cracks where the continent is being pulled apart. Together, these two arms are effectively isolating the Somali plate, like a perforation line on a sheet of paper. The continent is being pre-cut along a broad, precise path. But a rift of this scale doesn't just appear. It needs an engine, a source of power big enough to bend and break an entire tectonic plate. For decades, geologists argued over what that engine was. Were the plates simply being tugged from far away at the mid-ocean ridges where the seafloor spreads, or was something pushing from below? The answer came from one of the most powerful tools in modern Earth science: seismic tomography. Think of this like a CT scan for the planet. Every time a big earthquake happens, it sends waves rippling through the Earth. Those waves travel faster through cold, rigid rock, and they slow down when they pass through hotter, softer material. By measuring tiny differences in arrival times at thousands of seismic stations, scientists can reconstruct a 3D picture of what's happening deep underground, where the Earth is stiffer and where it's unusually warm. When they turned this technique on Africa, they found something huge. Deep beneath East Africa sits a giant low-velocity zone, a region where seismic waves slow down dramatically. It extends thousands of kilometers down toward the core mantle boundary. This is the African Superplume, a massive upwelling of unusually hot mantle rock rising from deep within the Earth. Think of it as a slow-motion blowtorch pressed against the base of the continent. For tens of millions of years, this superplume has been doing two key things. First, it can help lift the surface. Hot mantle is buoyant, so as it rises, it can support and elevate the overlying lithosphere. That's one reason much of East Africa sits on a broad, high plateau. The region has been swelled upward by processes acting from below. Second, and more important for the rift, it can weaken the lithosphere. Heat changes how rock behaves, warm the base of a tectonic plate, and it becomes less rigid, more deformable, more willing to stretch, fault, and thin, instead of resisting. And here's the key nuance. This deep upwelling doesn't have to act like a smooth, steady furnace. Geological and geophysical evidence suggests it can behave in episodes, periods when melt supply and pressure build, then release, then ease off again, which means events like the 2005 Dabahu rifting episode and eruptions like Hayli Gubbi in 2025 can be understood as surface flashes of a deeper system, a continent being heated, softened, and pulled apart from above and helped along from below. So, where does this story go from here? One of the most famous theories is the new ocean scenario. If the current rifting continues, eventually the land between the Nubian and Somali plates will sink low enough for seawater to pour in. We don't have to guess what this looks like. We can see the blueprint in the north. The Red Sea is effectively a baby ocean. Millions of years ago, the Arabian Peninsula was welded to Africa. As the rift unzipped, Arabia broke away, and the Indian Ocean flooded the gap. If you drained the Red Sea today, you'd see a textbook mid-ocean ridge running down its center, creating new crust and pushing the continents further apart. This is the future of the Afar region. Much of the Danakil Depression already sits below sea level. The only reason it isn't underwater today is a range of volcanic hills, the Danakil Alps, that act as a natural dam, keeping the Red Sea at bay. Evidence from coral fossils found in the desert shows that the ocean has breached this dam before, briefly flooding the depression before evaporating and leaving behind salt layers miles thick. As rifting continues, the crust beneath the dam will thin and sag. Eventually, whether through slow erosion or a violent earthquake, that natural dam will fail decisively. When it does, water from the Red Sea could roar into the desert in a matter of days, turning what is now sun-baked salt into a boiling inland sea. This new sea would separate the Horn of Africa from the mainland. The second possibility is less cinematic, but in principle, far more disruptive, because rifts don't always finish what they start. The Earth is littered with the ghosts of failed rifts, places where a continent began to split, and then the process stalled. One of the best examples sits buried inside North America, the Mid-Continent Rift System. About 1.1 billion years ago, a huge crack began to tear what is now the US and Canada apart, stretching from the Lake Superior region toward the Central Plains. Magma surged upward, pouring out as enormous basalt flows. For a while, it looked like North America might split. Then, it stopped. The rift stalled and was slowly buried, detectable today mostly through geophysical fingerprints like gravity and magnetic anomalies from the dense volcanic rock that filled the crack. Now here's the uncomfortable question. What if the East African rift doesn't cleanly evolve into an ocean basin? If the stretching slows or stalls but deep heat and melt supply keep rising, the system doesn't necessarily become quiet. In rare cases, it can become something else. A sustained volcanic outpouring, repeated eruptions over long periods, not a single volcano, but a region-scale flood of lava. A large, igneous province. These are rare events where lava can cover huge areas over time, hundreds of thousands of square miles, often accompanied by massive gas release. And that's the real danger, not the lava itself, but what comes with it. Sulfur aerosols, carbon dioxide, and other volcanic gases that can push climate hard in both directions. Short-term cooling pulses, followed by longer-term warming, acid rain, and ocean acidification. And yes, large igneous provinces show up in the geological record uncomfortably close to some mass extinctions. The Siberian traps, for example, are strongly associated with the end Permian Great Dying, when life on Earth suffered catastrophic losses. Now, to be clear, this is a low-probability scenario on any human timescale, but it's a useful warning. A failed rift doesn't always mean a harmless one. Sometimes it means the energy doesn't disappear. It finds a different way out. Even if this rift never produces a mass extinction, the rifting process can create some of the most bizarre and deadly phenomena on Earth. When deep mantle heat meets a continent that's being stretched apart, you don't just get earthquakes, you get chemistry that looks almost wrong. Take Oldonyo Lengai in Tanzania. It's the only active volcano on Earth, known for erupting nitrocarbonatite lava. A lava so unusual, it barely behaves like lava at all. Most lava is rich in silica, which makes it thick, sticky, and extremely hot. But Lengai's lava is rich in sodium and potassium carbonates. It erupts at around 1,000 degrees Fahrenheit. In volcanic terms, that's cool. And it looks cool too. Instead of glowing red, it can look like moving black mud or motor oil. It's so fluid, it can rush downslope faster than a person can run. And when it cools, it doesn't become the familiar dark volcanic rock. It weathers into a pale, chalky powder that can look like snow. Then there are the killer lakes. In the western branch, lakes like Kivu sit in deep rift basins above active geology. Volcanic gases seep up from below and dissolve into the deep water. Over time, the lake becomes a storage tank. Estimates suggest Lake Kivu holds hundreds of cubic kilometers of gas, roughly 300 cubic kilometers of CO2 and 60 cubic kilometers of methane, depending on the study. As long as the lake stays stratified, layered, with dense bottom water, sealed beneath lighter water, the gas remains trapped, like pressure held down in a sealed bottle. But if something disrupts that layering, a landslide, an earthquake, or volcanic activity, the gas can suddenly come out of solution in what's called a limnic eruption. We've seen this happen. In 1986, at Lake Nyos in Cameroon, a sudden release of CO2 produced an invisible cloud. Because CO2 is heavier than air, it didn't rise. It poured downhill, hugging the ground and moving through valleys. In minutes, it killed over 1,700 people and roughly 3,500 livestock, suffocating them where they stood. Lake Kivu is a different category of risk. The stored gas volumes are far larger than Nyos, and Kivu isn't isolated. Millions of people live along its shores. That's why the lake demands constant monitoring and careful gas management projects, including controlled extraction and degassing. In the rift, danger isn't always loud. Sometimes it sits quietly under the surface, held in place by nothing more than a stable layer of water. And here's the twist. But the rift isn't just a destroyer. It is also a creator. In fact, you wouldn't be watching this video if it weren't for the East African Rift. Many anthropologists believe that this specific geological violence is what created us. Millions of years ago, as the East African Rift began to form, it shattered the landscape. It turned a flat, uniform rainforest into a complex mosaic of cliffs, lakes, and savannas. This chaotic, changing landscape forced our ape-like ancestors to adapt. This is known as the pulsed climate variability hypothesis. The idea is that the rift didn't just create one environment, but a landscape that fluctuated wildly between wet and dry, forest and grassland. To survive, early hominids couldn't just be good at one thing. They had to be adaptable generalists. In a world like that, being specialized is risky, but being flexible is an advantage. That's the core of variability selection. Traits that help you handle change, diet flexibility, movement across mixed terrain, problem solving, get rewarded again and again. And the rift didn't just shape the habitat, it also preserved the evidence. Rift basins collect sediments, and volcanic layers act like timestamps, helping scientists date fossils and artifacts with unusual precision. That's why names like Afar matter to human history. Lucy, Australopithecus afarensis, about 3.2 million years old, was found right here in Ethiopia's Afar region. A small-brained creature, but already adapted for walking upright, proof that bipedalism came early, long before big brains. So yes, volcanoes, earthquakes, gas-charged lakes, that's the rift today. But millions of years ago, the same forces may have turned East Africa into an evolutionary obstacle course. And in a landscape that kept changing, the winners weren't the strongest. They were the most adaptable. Today, the rift offers a new kind of gift: energy. The same deep heat that threatens to reshape the continent is also an extraordinary source of geothermal power. Reliable, low-carbon electricity drawn straight from the earth. Kenya is already one of the global leaders in harvesting it, tapping rift zone heat to generate electricity at scale, over a gigawatt of installed geothermal capacity, and a major share of the country's power coming from this system. Ethiopia is following suit. There's a profound irony here. The forces that once reshaped the environments early humans had to survive in are now helping power their modern descendants. Yes, we can turn a portion of the rift's heat into something useful: electricity, stability, growth. But the rift doesn't stop being a rift, which means geothermal isn't a happy ending. It's a relationship, learning to live on a moving boundary and to benefit from it without forgetting what it can do. Hayli Gubbi is that lesson in real time. On the ground, herders downwind watch ash settle onto the grazing land their animals depend on. In the sky, scientists track a gray plume stretching thousands of kilometers across the atmosphere. And it points to a truth we often forget: the map of the world is not permanent. We tend to think of the continents as solid, immovable, and eternal, but they are not. They are restless rafts of rock, constantly drifting, colliding, and breaking apart on a sea of magma. Africa is splitting today, but in the distant future, the Atlantic Ocean may close. A new supercontinent may form. The map we know is just a snapshot in time. We will never see the fully grown ocean that may one day flood afar. We won't stand on the beaches of the future island continent of East Africa. But knowing that this process is underway changes how we see our planet. It reminds us that our lives are brief, fragile flashes set against deep time. From orbit, it's beautiful. On the ground, it's precarious. But right now, we have a front row seat to watch the opening act of a story that will outlive our species. If you could fast forward 10 million years, what do you think the new East African continent would look like? A tropical paradise or a volcanic wasteland? Share your predictions in the comments below. To untangle more of the hidden forces that shape our world, subscribe to World Untangled and join us for our next deep dive.